Let's do a lever calculation example. Have this be our first problem. I'm going to read the problem to you, and then we'll answer some questions relating to this problem. So here's the question. Well, here's the facts. A first-class lever in static equilibrium has a 100-pound resistance force and a 22-pound effort force. The lever's effort force is 6 feet from the fulcrum. Starting from the beginning, it's a first-class lever, so we want to draw that. It's our starting point for this problem, is to make a picture. So we have a lever. It's first class, therefore the fulcrum someplace not on an end. And then every one of these pictures, if it's a first class lever, is going to be the same. We're going to divide this up into two parts. On one end, we're going to have the force of the resistance. On the other end, we're going to have the force of the effort. Once again, this picture so far is true of any first-class lever. We're going to also have the distance of the resistance, which is going to go from the fulcrum to the force of the resistance. And we're going to have the distance that the effort is to the fulcrum. This picture is going to be used for every first-class lever. Well, let's take the information that I said, and we're going to repeat that. It says there's a 100-pound resistance force. Well, let me write that down. We have the force of the resistance. It's 100 pounds. We're also going to have to figure out or be given distance of the resistance. And then we're going to have the force of the effort, and then the distance of the effort. Reading this again, there's a 22-pound effort force. So force of the effort is 22 pounds. That's 22 pounds, not 221. I didn't write that very well. Maybe that's better. And then it says that the lever's effort force, so distance of the effort force, is 6 feet from the fulcrum. So the distance of the effort is 6 feet from the fulcrum. We're going to take that information and put it into this picture. Fulcrum's resistance, I'm sorry, not fulcrum. The force of the resistance is 100 pounds. The force of the effort is 22 pounds. Let me clean this up here. And then we have the distance of the effort, which is 6 feet. If given the choice between making this picture small or making it big, it's in your best interest to make it big. Another thing I need to add to this picture is these forces are pushing down on the end of the lever. So here's all our information. Here's a picture. So let's say the first question is the following. What is the actual mechanical advantage of the system? So we'll say part A of this is to find the actual mechanical advantage. To do so, we're going to use the actual mechanical advantage formula. Actual mechanical advantage equals the force of the resistance divided by the force of the effort. In this problem, the force of the resistance is 100 pounds. And the force of the effort is 22 pounds. Please note, every time you use a number in this class, it needs to have a label, anytime you put it into a formula. When dividing something by itself, the answer is always 1. Pounds divided by pounds is 1, which means we don't have a label anymore. If you take 100 divided by 22 using a calculator, you will get to the nearest hundredth 4.55. The actual mechanical advantage is 4.55. As a ratio, you could say it's 4.55 to 1. You don't have to. It looks like this guy's kind of sad, kind of happy, in between. Wasn't the point. Supposed to be a ratio. So actual mechanical advantage is 4.55 to 1. Let's say part B to this has the following question. Using the static equilibrium calculations, so at the beginning this problem said it was in static equilibrium, which means it's perfectly balanced. Using static equilibrium calculations, calculate the length from the fulcrum to the resistance force. But what that is asking is for you to find the distance of the resistance to the fulcrum. Find dr. Well, to do so, if it's in static equilibrium, then that means the following. That means that the moment of the resistance is equal to the moment of the effort. If those are equal, it's perfectly balanced. The moment of the resistance is defined as the force of the resistance times the distance of the resistance. The moment of the effort is defined as the force of the effort times the distance of the effort. Now we simply have to use these numbers that we see up here and just substitute them into this problem, and then use our algebra rules that I hope that you all know. The force of the resistance is 100 pounds. Remember, every number that you substitute gets labeled. Distance of the resistance, we don't know. Force of the effort, 22 pounds. Distance of the effort, 6 feet. So here on the right, we are multiplying. 22 times 6 is 132. Pounds times feet is foot-pounds. On the left, there's only one number, so we can't change our number, but we're going to have 100 pounds times d sub r. Trying to get d sub r by itself, so we're going to divide both sides by 100 pounds. On the left, it gives us d sub r. On the right, it gives us 132 foot-pounds divided by 100 pounds. Once again, your pounds are going to cancel. When you divide something by itself, it cancels. Now we have 132 divided by 100. Which is 13.2. And the only label that's left is feet. So to answer this question, what is the distance from the fulcrum to the resistance force? It's got to be 13.2 feet. And I divided that incorrectly. It's not 13.2, it's 1.32. I apologize for that. 1.32 feet. And here's why 13.2 doesn't make any sense. If you look back at this picture, the more force you have, the less distance you need. The less force that you have, the more distance you need. So having 100 pounds and 13 together doesn't make any sense when the other side is 22 and 6. So it's 1.32.